When does a Taylor series, or Maclaurin series for that matter, converge? It turns out as the limit as n approaches infinity of the remainder is equal to 0, then the Taylor series converges and it equals the function itself. So remember, the remainder is r sub n, is the n plus first derivative, so it's the next derivative, evaluated at some point z, and z is in my interval, times x minus e to the n plus 1 divided by n plus 1 factorial. So just think of it as you're doing an nth polynomial expansion of Taylor, and then you look at the next term. So let's look at these approximations of sine of x. When you have a first order approximation, it's pretty close, it's pretty accurate, fairly close. But when you get farther away, of course, it's not very accurate at all. The next order, the P3, it agrees very closely for a longer period of time, or a longer values of x. The same thing for 5 and 7. You see they begin agreeing more and more. But the question is, does this actually converge to the function? Now, if we were to show that this series converges for all values of x, what we have to do is look at the expansion itself. Remember, sine of x, we've already done this one, is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7th factorial. Now, what you always want to do is look at your nth term, or in this case, your n plus 1 term. Minus 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial plus, and we're going to keep going. Now, I know the n plus 1 derivative is either going to be plus or minus sine x, or what is it going to be? Or it's plus or minus cosine x. It's one of the two. So I know that no matter what, the next derivative is less than or equal to 1. You match the values there. So I know that this derivative is bounded by 1. No matter what number I put in there, no matter what x I put in, I know that this is going to be less than 1. Therefore, for any z I pick in my interval, I know that the n plus first derivative of that is also going to be less than 1. So let's look at Taylor's theorem, and let's look at what the remainder is going to look like. All right, so this is equal to the n plus first derivative evaluated at some point z times x to the n plus 1 divided by n plus 1 factorial. All right, now I know that this is always less than or equal to 1, so this is going to be less than or equal to the absolute value of x to the n plus 1 divided by n plus 1 factorial. Now, we know that the limit as n goes to infinity of the absolute value of x to the n plus 1 for a given fixed x divided by n plus 1 factorial, we know this is 0. So we can use the squeeze theorem for all x and say that the nth derivative, or the remainder of x, goes to 0 as n approaches infinity. So by the theorem, we know that sine of x, the Maclaurin series for sine of x, converges to the sine of x for all x. Now, in general, guidelines for finding the Taylor series, just a brief review: differentiate several times and evaluate, make a table, look for patterns. use a sequence developed in the first few steps of the Taylor coefficients. A sub n is the nth derivative evaluated at c divided by n factorial to find your interval of convergence and your power series. And then within that interval, determine whether your series converges to f or not. How? You look at the limit of Rn, limit as n goes to infinity of the absolute value of Rn. All right? If that equals 0, then it converges. If it doesn't, the series does not converge.